Swayam Prabha. Digital India. Educated India.
So let's get started with the second part of the this lecture. This is focused on generalization of some of the concepts that we started off developing with 2-hour manipulator kind of a case. Okay, so general mechanical system, if we consider how its Lagrange formulation gets developed and what are the properties corresponding to that. Okay, so we'll just go back and notice once again the expression for the kinetic energy that we got. Okay, so let's go into the slides. Okay, so you see this kinetic energy expression that was there for 2-hour manipulator was expressed in these terms of this D11, D12, D22. Okay, so this is part of this kinetic energy expression, total kinetic energy expression. Okay, so this is you can see that from your equations derived here. Okay, so here you can see that the kinetic energy is expressed in this D11. Now this D12 is basically this D0 by 2 term. This D0 is given here, expression is given here. So this D0, D11, D12, D21 and D22, these are like 4 terms in this kind of a quadratic form matrix, and then you have this Q1 dot Q2 dot multiplying here. Okay, transpose and the Q1 dot Q2 dot. Okay, so this is like a quadratic form of expression for kinetic energy. Okay, and you will find that all the mechanical systems kinetic energy can be expressed in this kind of a form. Now this form gives us a clear indication that this matrix which forms this kinetic energy by this quadratic form matrix is going to be positive definite. Okay, can you see that why it is going to be positive definite? Pause for a while and check, like, see why this matrix need to be positive definite, because this is a quadratic form. If you express for a quadratic form of a matrix, okay, then if the quadratic form has a value which is greater than 0, quadratic form is a scalar value. So that value is the greater than 0, then the matrix is positive definite, right? So the kinetic energy of any system, okay, will always be positive. Okay, from that simple kind of a physical analogy, one can see that this matrix is going to be positive definite. Okay, so this one of the properties of this matrix for D is it is positive definite. Okay, now you can see that the same matrix appears in the final expression of the equations. So this equation 1, if you see this term here, this is D11 Q1 double dot and D half D0 or D12 Q2 double dot. Okay, these terms appear here as well in one equation, and in the second equation it's again half D0 or D21 Q1 double dot and D2 to Q2 double dot. Okay, so these are this is a way this D matrix appears in the final equations. So the moment you write kinetic energy, you know the part terms of the final equation. Okay, even the second part has some kind of interesting mathematical expression in terms of this D matrix as well, and maybe you have a potential energy terms also coming in there. So we'll see that. So this can be generalized in general for any mechanical system. Okay, when you say mechanical system, what we mean is that the systems which are expressible in the form of a kinetic energy for mechanical systems. Okay, so we'll just get a little bit details into that now. So let's go back to our slides. So as we see, this kinetic energy gets expressed in terms of this D matrix, and this D matrix now is positive definite. So up to that we see why the D matrix should be positive definite. Now let's generalize this in general for kinetic energy of several rigid body mechanical systems. Okay, so to some extent it may be valid for even flexible body mechanical systems if we restrict the discussion about them to a finite number of modes. So let's not worry right now about flexible body system, but we'll just get into the rigid body system dynamics. So for a rigid body, the kinetic energy is expressible in this form. Kinetic energy is actually summation of all these different mass elements in the system and corresponding velocities of the CGs of the mass elements, and then inertia of those elements and corresponding rotation kinetic energy part. Okay, so corresponding omega for that element. And summation of all such elements over this should be summation here over all different bodies will give you total kinetic energy of the system. Now this kinetic energy we need to express in the form of a generalized coordinates. Okay, so this kind of a quadratic form for in the generalized coordinate it can be expressible. Okay, so this is possible by expressing, as we have seen in 2R manipulator, the velocities of CG and omegas, they should be expressed in generalized coordinates, and you'll have this expression possibility. Okay, once we do that, you get this kinetic energy as some summation of this qi qj dot elements and dij. Now we start off with our Lagrange formulation based on this expression. Okay, let me give a check once if we are okay with the recording. Just pause for a while, and you start doing this using this kinetic energy expression and deriving the some terms in the Lagrange formulation. We'll come to that immediately. So if you see these terms, so if you take this term, okay, first term, so what we do is see potential energy in the system, okay, is a function of the q's only the generalized coordinate or degrees of freedom variable, and not its derivative, okay, or q dot. Q dot is not appearing in the potential energy term. So notice this is important. So this is a q is a vector. It may be all dependency on all generalized coordinates, but the derivative of q will not appear in the potential energy terms in general. Okay, for a mechanical rigid body systems. Okay, then now if we see we start taking first partial derivative of L with respect to q dot. Okay, so this will have this form. Now how this form comes, okay, you need to think about that. It's not like straightforward or trivial to directly this will be there. No. So what we are doing is we are expressing these energy terms in dij q dot I q dot j. Now if you form these terms or look at these terms in the matrix, where are they? And then you see, if I take the partial with respect to say q1 dot here, okay, so any k q1 dot, then what terms are going to appear is what we are looking in this expression. So if we see this D of Q matrix, that has these terms. Okay, now I'll write these terms with the multiplication, so that we have summation of all these terms coming in the derivation. Okay, Q1 dot, Q1 dot. Okay, then D12 Q1 dot and Q2 dot. Like that there will be terms D13 into Q1 dot, Q3 dot. Okay, and here D21 again Q2 dot and Q1 dot is again coming here. Okay, so notice that this Q1 dot is coming here. Like that D31 Q2 dot and Q1 dot is coming here. Okay, so this is how like the terms are going to come for Q1 dot part of it. Okay, so when I take so this will continue and so on and so forth, and you'll have all these terms are actually summed up in the final expression for so we are not saying just dq. This is not really just a dq. Okay, so this is misnomer. It's a dq and like there's some kind of a quadratic part multiplication. Okay, so and this is summation of all these elements which will happen in the final expression. So you will have also here q dot transpose dq q dot. That kind of a expression we are writing, but we are not writing as a summation, but like we are not writing the plus signs, but we are just putting these elements in place so that we know which of the terms are going to appear when I kind of do the partial derivative with so if I take this partial now, partial of dq or not actually dq, sorry, this partial of kinetic energy with respect to dq1 dot. Okay, so this one is actually k now from our previous expression for generalization purpose, and in here there are going to be terms which are based on so the terms will come from both places, from here also and here also. Okay, so this d1 d21 and d12 are same because this is a symmetric matrix. Okay, so this matrix is not only positive but it also is a symmetric matrix. Okay, so why it is symmetric? Like you'll see that any quadratic form can be rearranged to get into a symmetric kind of a form. Okay, so one can kind of see from there this will get into a symmetric matrix. So if it is not symmetric, we can kind of like turn it into a symmetric matrix. Okay, so these are like cross these are like what you say cross diagonal terms. They are not like non-diagonal terms, and this is a diagonal term. Diagonal term, if you see this is derivative with respect to q1 dot, it will be like 2 times like so this derivative is going to be this diagonal term will have 2 times d11 okay q1 dot. Okay, and off diagonal terms will have like 2 again, because if you see here this kind of a term and this term will get summed up, and because they are symmetric with respect to each other, because the matrix is symmetric, like these both the terms are equal, and that's why this is 2 times d say 1 2 into q1 dot again. Okay, sorry, this is going to be q2 dot. When I take a derivative with respect to q1 dot, the q2 dot will appear here. Here it is q1 dot because like it is q1 dot square. Okay, so now there is a half in the kinetic energy expression. So what we are writing is only for part of this term, del QE, del kinetic energy by del Q1 dot, which is now corresponding to first diagonal, first term and its derivatives that will come. Because now we are considering with respect to say q1, which is k is now equal to 1, so this will be in general summation of now, you can see that the half will get cancelled out. Okay, so when half gets cancelled out, you get this d now um, dkj. Okay, so k is my term which is here. So d1 d12 like that, I'll write in terms of dkj and q j dot. So if you see this where j is equal to 1 to n. Okay, so for k is equal to 1, if I see, then j is equal to 1 to n, like this qj dot will give me this expression for the first partial derivative of kinetic energy with respect to q1 dot. Okay, so clear this part. So like that you need to see and move on from here. Okay, so let's see this expression. Okay, this is dkj qj dot. Okay, that's what we have seen. Okay, so this is how you need to, it's not, don't consider this to be a trivial exercise. This is one has to kind of think about in terms of the expression for the matrix, and then the terms coming from the quadratic form, and then take them further to differentiate. Okay, like that we do now for so you can do further for other terms now, like say d by dt of del L by del Q dot and del L by del Q. Okay, these kind of terms you can express now in a similar kind of a fashion, and try yourself first doing that, and then only you can go ahead and look at the further part of the lecture. So please do this, that is an important part of the exercise to get to the real understanding of what is happening. And even if you have a difficulty, no problem, like you can get stuck, no problem. Getting stuck is a very important step in the understanding, and once you get stuck, then you come back and look at how things are done, and then maybe things will be better clear. Okay, so if we move on for further differentiation, so you can see this is a term coming because of the complete differentiation with respect to time for the same term. So you can see here this part first, there are two derivatives that will come because of the multiplication. So first is the derivative of this qj double dot. Okay, so qj dot term will get differentiated to give you qj double dot, and then you will come to the differentiation of dkj. Okay, now you can see that this first term yields you directly like a term in the final equation. Okay, dkj qj double dot. Okay, this is a term that will appear in the final equation, because now we'll assemble these terms when this complete derivative, this is no more derivatives will be executed after this. So there are this after this there is just assembly of the terms. Okay, and then if you see this term, okay, this term can be expressed as another summation now. Okay, so this d by dt of dkj of generalized coordinates vector q function of that. So we take partial with respect to q, and then q dot will be multiplied, and that's how this becomes now this summation still remains, but inner this derivative can be expressed as a summation over I, and the summation over j is already there, so this becomes like a summation over both I and j, dkj, d del kj del qi, and qi dot qj dot. This kind of a term will come. Okay, this you can work it out, and again do the way that I have expressed in the form of like in this matrix form with all the terms written there, and then things will be clear for you. Okay, so we'll consider it that way. Now for del L by del Q, you have these terms coming up. Okay, and again these terms are like quite straightforward to see probably. Okay, because this is already from the kinetic energy, we'll have this term coming. Okay, we are just taking partial with respect to q, so this is a partial with respect to q kind of a term, and then this del p by del q again here. Okay, so I would request you to kind of go through clearly in all expanded terms in the matrix kind of a form, and then things will become a little more clear how we are expressing this. Okay, so now if we move on assembly of these terms, we get this kind of a assembly. You just put this together here in this complete equation, and you get these terms assembled, okay, in this form here. So by interchanging the order of summation and using some kind of a symmetry in the system, again this is not very trivial to see directly. One has to kind of write these terms in ij, proper consideration of ij k, and then you will find that this can be written by rearranging. So this symmetry is used to kind of get this split part of the term, something like that. Okay, and this kind of helps in some definitions later. That's why this is done. I mean, so this C, actually this is your C part of the term. Okay, C matrix, if you want to say, or like some kind of a correlates and centrifugal kind of components which are coming in these terms. Okay, their derivatives and things like that. Okay, yeah, so kinetic energy derivatives actually give you this centrifugal and Coriolis kind of a force terms here. When q I is equal to j, you will have a q dot square term that is coming, which will relate to somewhat like a centrifugal force term, and when I is not equal to j, there will be like a Coriolis terms. Okay, now by doing this, like some kind of a readjustment is done for this particular term only, and you get this expressed in this form. Okay, and further you can express that in terms of this C I J K kind of coefficients. Okay, these C I J K coefficients sometimes are called Christoffel symbols. Okay, so there is a mathematical kind of a jargon there, but let's not worry about that. It's basically like you get this kind of a C matrix multiplying some Q dot, and this T matrix we know already, and Q double dot, and these potential energy terms are clubbed into this G matrix, and then you get this complete expression for your final equation of motion. Okay, so this is how things happen here. So let's now see. This form has some certain other property. Okay, so these important mechanical properties that we have seen for important mathematical properties that we have seen for this mechanical system. First is D matrix is symmetric and positive definite. Now this is the other property. okay, this D matrix D dot minus 2C, okay, is Q symmetric. So you see that this C matrix can be developed in many different kind of ways. Okay, given this as a quadratic form here, okay, I can have like different combinations of the terms coming to get it out to kind of find okay, no, this is not a quadratic form, sorry, this is a quadratic expression, but we are not considering here the quadratic form. Okay, so here the form is just C matrix multiplied by a vector. So for this, by rearranging terms in C, we can have different possibilities for C matrix. It's not a unique. Okay, so maybe we can see that with respect to our example of to our manipulator. So we go back to our manipulator case. So let's get here. If you see this C Q dot term, okay, so this is a C Q dot term as a vector form. So this is, say this has some terms as 2m2 L1 this is Q1 dot kind of a Q1 Q2 dot term, then Q2 dot square term and Q1 dot square term. Now I can say like so I can choose to express like this is like CQ dot. So what should be the C matrix? I can have different possibilities. Okay, so one of the possibilities you can see up here, I can say my C can be expressed as so I have used some symbol. So just to kind of get rid of these complicated terms coming there, I am just using this H as a symbol for some term. Okay, so this Q2 dot, okay, so this is like 2H Q1 dot Q2 dot H Q dot square, and minus H Q dot Q1 dot square is like C times Q dot term. Actually, this Q dot is missing here. Okay, so I'm kind of trying to get my C matrix from here. Okay, so so this is my C Q dot term, and this is actually C matrix, one of the possibilities. So what I have done is like we can see that now this term is going to multiply in the first row by Q1 dot. So this H Q1 Q2 dot Q1 dot plus now this H Q1 dot square, okay, and H Q2 dots okay, no, H Q1 dot, this is the second term of the matrix. So this H Q1 dot Q2 dot and H Q2 dot square. Now this H Q2 dot Q1 dot and H Q1 dot Q2 dot is the same term. They will get added to 2H Q1 dot Q2 dot here. See the way it is split. So this term is split into two parts. One part is put in this side, another part is put on the other side. Okay, and then like this is getting multiplied by Q2 dot when I have a multiplication Q1 dot Q2 dot as a vector here. Okay, so this term is getting multiplied by Q1 dot alone, and this term is getting multiplied by Q2 dot alone. And then like when I add these two terms as a first term of the matrix vector product, then like I'll get to H Q1 dot Q2 dot as we want up here. Okay, like that you can express similarly like HQ1 dot term here, HQ1 Q1 dot square term, HQ1 dot here, and nothing here. Okay, so there is no Q2 dot term appearing there. So like that we can this is one possibility of arrangement. Okay, there can be other possibilities of arrangement also. Okay, so I could have just said okay, this term this part of the term to be 0, and in here I would say this is 2 times HQ1 dot. That also would have been a possibility. Okay, all these diagonal terms are going to be 0, and like I combine these 2HQ1 dot Q2 dot on this side, or I could say okay, I will use 2HQ2 dot here and I don't use this term here. I just have this term to be equal to HQ2 dot. So there are multiple possibilities for assembling this C matrix to get the same expression CQ dot, okay, as a vector. So my choice of this is going to be in a way so that like I use it for this property d dot minus 2c to express. So by expressing in this kind of a form, and I see this d dot minus 2c, so d expression is here, so d dot expression is this, okay. Again, by using this h as this value here, so I have used h to be equal to say minus m2 l1 c lc2 sine q2, okay. If I use that as a h value, then I get d dot is equal to some part, and when I take d dot minus 2c, it gets into the skew symmetry form. Okay, so you just do it yourself starting from scratch, and then like come to understanding of this. It's very important to get to because many times you will need to do this kind of a little bit mathematical manipulation to see how to make sure that okay, this once you have d dot, using this d dot in some way to make sure that c is expressed in such a way that d dot minus 2c gives you skew symmetry. Okay, so this exercise would be interesting to do to understand like how this can be further generalized. Okay, so I'll leave this to you for generalization kind of a case. I will not kind of get into generalization. It's just a little bit of mathematical jugglery that I think you guys can do really nicely. If at all need be, maybe we can go through that, or maybe I can post the expressions or the derivations. Okay, so let's get back to our slides again. Okay, so this way we defined this C matrix in this. This is one of the kind of a rearrangement is done to kind of get to this form, and in this form you will find that when you define C matrix in this kind of a form, you get this property d dot minus 2c to have a skew symmetry. Okay, that can be derived and shown. We'll not get into the depth. We'll see now how we can use this form to further get to a control for these kind of a systems. So rigid body systems control, when we see that time, we'll be using this property of skew symmetry and the property of D to be positive definite matrix. And one can see now, if you go for the simulation, then for simulation you need this q double dot to be expressed as a function of q's and q dots, and for that you will have to push this or these terms like on the right hand side, c term and g term on the right hand side, and then entire expression on the right side you need to multiply by d inverse to isolate these q double dot terms. Once you isolate them, then only you can use them in your simulation for getting the ODE45 simulation going. For the simulation, you'll need these q double dot isolated terms. Okay, so vector isolation, isolated vector you can get by this D inverse matrix multiplying all the terms which are pushed on the right hand side of this equation. Okay, and that's how one can get going with the simulation of such complex systems. Okay, which are in general like having these cross diagonal terms or off diagonal terms to have cross coupling between different variables that are there as a generalized coordinates in the system. Okay, so this is how things go for the general mechanical system, and these properties are going to hold for mechanical systems for sure with rigid bodies, and this is important time invariant mass. So the mass is not changing with respect to time. Okay, there these properties will hold true. Okay, so when the mass is changing with respect to time, then we'll have to again recheck and make sure that okay, this will happen. or not, because we have so far in the thing we have like no dependency of D on the time is considered explicitly. So it is implicit in Q is fine, no problem, but explicit dependency of D matrix on time is not considered in the whole derivation. Explicit dependence of kinetic energy on the time. D matrix is just a part of the kinetic energy. So this kinetic energy expressed as a time as a function of explicit function of time is not considered in this derivation. That's why we cannot say these properties will hold for time invariant time varying mass. These are like so far valid for time invariant mass. So one can see what changes it may have and all so and so forth. That can be a matter of further discussion. Okay, so this is how we proceed with base development for general mechanical systems. Okay, so all the mechanical systems with n rigid body, so robotic systems are a part, any mechanism is a part. Okay, so everything is covered under these edges of this Lagrangian formulation, and what we don't have so far here is the damping terms and any other kind of forms of terms which are energy consuming. Okay, so those terms are going to be forming like these external forces in the system. So as a damping, as we saw, the damping will form this external torque in the system. Okay, and they will come appear here, external torques that you are applying or external forces that you are applying. So this tau is just a term, but it can be in the force or it can be in the torque form or moment form or whatever form. Okay, in the direction of this generalized coordinate. Okay, if the generalized coordinate is a linear kind of a quantity, like the x, then this will be force. If the generalized coordinate is theta, the rotation kind of quantity, then this will be actually a torque. Okay, so these torques in the direction of generalized coordinates, okay, they need to be added. The damping and other terms can be added into those parts. Okay, so that's how we'll proceed with the mechanical system derivation.